Now we get to talk about derivatives. Earlier, we learned a little bit about the derivatives when we talked about the instantaneous rate of change. You can think of the derivative as the instantaneous rate of change at a single point. Again, it's like the rate of change at a single point. Again, it's the slope, of the tangent line at a single point. Now, a derivative can be described as the rate or velocity at which our output value, which we normally think of as y, increases or decreases per 1 unit increase of our input. This is important. It's just 1 unit increase, which means the units of a derivative are going to be like the units of a slope. It's an increase or decrease of, for example, people per year or dollars per month. If we look at the limit definition, we would use this notation, which is f prime, and this is also our rate of change, where we take the limit as h approaches 0 of f of the quantity x plus h minus f of x, all divided by h. You may recognize this as the difference quotient. There are several different notations for the derivative. You may see it as y prime or f prime of x, dy over dx, or d over dx of a function, say f of x. Now, the notation dy over dx is called the Leibniz notation, and it's read as the derivative of y with respect to x. And remember that x can have just a small 1 unit increase in x in the interpretation. Now, some of the notations for derivatives are asking you to evaluate it at a particular input value, and they may look something like this: f prime at 5, or the derivative of y with respect to x at x equals 5. In order to understand how to find derivatives and where to find derivatives, it's very helpful to know where derivatives do not exist. Think of non-differentiable function values to be at places on a graph where you cannot draw a tangent line, or the slope of the tangent line is undefined. For example, in this first graph, we have what's called a corner or a cusp. If we were to draw a line right here at the point where x equals a, we can't snuggle that tangent line up to a curve. There is not an exact slope at that corner or cusp, so the derivative does not exist at x equals a. In our second graph, there's a discontinuity. Now, those discontinuities can also include holes, but basically, if it's at an endpoint, we cannot draw any specific tangent lines at those points, so the derivative does not exist. In our very last graph here, if there is a tangent line that's vertical at that x value, remember the slope of a vertical line is undefined, therefore the derivative is undefined.